Good morning, gentlemen. We interrupt your curriculum at AP Chemistry for a short little unit on gases. The chemistry of gases is chapter 5 in your textbook and chapter 5 in your study guide. The problems in your study guide are going to be really helpful. This is an introduction to gases, so I'm going to go through some facts really quickly and do some simple sample problems to get us started. First of all, what we know about gases already. I hope we can start with your prior knowledge and build some learning from there. You already know that the noble gases, helium, neon, krypton, argon, xenon, and radon, are monatomic gases. Hydrogen, oxygen, nitrogen, fluorine, and chlorine are diatomic gases. They're part of that group of diatomic elements, and these are the ones that happen to be gas. What you may not know or haven't thought about was all the covalent compounds that are actually in the gas phase at standard temperature and pressure. It's going to be helpful for you to be able to recognize these so you will know when you can use gas phase stoichiometry or other functions about gases. So ammonia is a gas at standard conditions, methane, hydrogen chloride, hydrogen fluoride, and hydrogen bromide are gases at standard conditions. Normally we see these as acids, but those are when they are in the aqueous phase. So when HCl is dissolved in water, it becomes hydrochloric acid. Hydrogen fluoride in water, hydrofluoric acid. Hydrogen bromide in water, hydrobromic acid. Nitrogen monoxide and nitrogen dioxides are found in the atmosphere, as is sulfur dioxide. These are all common pollutions or pollutants. Hydrogen sulfide, hydrogen cyanide, and of course you know carbon dioxide and carbon monoxide, the last two here. The point is all of these are covalent compounds. They're all small in molar mass. They are all gases at standard conditions. We're going to start talking about things you probably already know about the properties of gases. First, gases are less dense than other states of matter. This seems pretty obvious. Less dense than a liquid and certainly less dense than a solid. But let's try to quantify that. Here I have a little beaker with 1 mole of water. 1 mole of liquid H2O takes up 18 milliliters of volume. Water has a density of 1 gram per milliliter, and water has a molar mass of 18 grams per mole. So 1 mole of liquid water will take up 18 milliliters of volume. But boil it or evaporate it, expand it into a cloud of water vapor, and that H2O gas takes up 22,400 milliliters of volume, over 1,200 times more volume. This proves that any gas sample is mostly empty space. The particles take up very little volume in a typical gas sample. So like a mole of water is 1,200 more times volume than the same amount in liquid, proves to you that any gas sample is mostly empty space. Next thing we know. The volume of a gas will expand or contract depending on pressure and temperature. Temperature of a gas matters. Pressure of a gas matters. Let's look at this example. Many of you remember when we had the visiting scientist come in with this big vat of liquid nitrogen, and he blew up a balloon, and the balloon full of gas particles shrunk because the liquid nitrogen was at low temperature, minus 70 degrees Celsius. But when we took the balloon out into the room temperature, the higher temperature transferred kinetic energy to the gas particles inside the balloon, and the balloon's volume expanded. So the volume of that balloon depended on what temperature condition it was in. Gas depends on pressure and gas depends on temperature. So I'm going to have a quick word with you about the temperatures of gases. When we calculate gas properties, when we calculate gas equations, we use gas temperature measured in Kelvin. So gas temperature is measured and calculated in kelvins. Remember, Kelvin is the absolute temperature scale. Every degree Celsius is the same size as a degree Kelvin. But to convert from Celsius to Kelvin, you have to add this factor, 273. 0 degrees Celsius, the freezing point of water, add 273, that would be 273 Kelvin degrees. If you're given a temperature in Celsius and you're using it in a gas calculation, you're going to have to convert it to Kelvin. So let's give you a couple of conversion practice problems with temperature. So here's the first one. Convert 25 degrees Celsius to Kelvin. This is simply adding 273. 25 plus 273 is 298 Kelvin. 298 is a typical room temperature. Second problem. Convert 50 degrees Kelvin to degrees Celsius. That simply becomes a subtraction. 50K minus 273 equals negative 223 degrees C. Now 50K is roughly the boiling temperature of many elemental gases. For example, fluorine boils at 53 Kelvin. So that's about negative 220 degrees C. You have a practice problem on your worksheet to do. I'm going to move on now to talk about standard temperature. When we compare things in chemistry, we have to do things at the same conditions. So one condition is standard temperature. Standard temperature is 273 Kelvin. That means standard temperature is 0 degrees C, roughly the melting point or freezing point of water. So about the temperature of ice cubes is standard temperature. We also have to talk about standard pressure. Temperature matters for gases and pressure matters for gases. So when we compare gases or when we use them in reactions, often we refer to standard pressure. The International System of Units lists Pascal as the unit of pressure. So standard pressure is 101,325 pascals. That's a lot of pascals. That's a really big number to work with. So we typically work with 101.3 kilopascals. kPa will be found in a lot of different problems you'll work with. This pressure in kilopascals is equivalent to a column of mercury that is 760 millimeters tall. Seems kind of strange, but there are instruments, including one in our classroom, that is a column of mercury that is open on the bottom to the atmosphere. And the atmosphere pressure in the atmosphere pushes down on that column of mercury, and the mercury is able to elevate up a tube to a distance of 760 millimeters when the pressure is normal 1 atmospheric pressure. When it's a little high pressure, it'll be 761. When it's a little low pressure, it'll be 750. So we can read the barometric pressure using a column of mercury. Some problems will call that column of mercury torr, 760 torr. But all of these are equivalent to 1 atmosphere of pressure. And 1 atmosphere comes from the pressure on Earth at sea level with exactly 1 of the Earth's atmosphere over the top of your head. You might have to do some pressure conversions. They might give you pressure in one unit and you will need to use it in another. So let's do a little pressure conversion practice. I'm going to cover this now. This problem says, an airline maintains cabin pressure during flights at 788 millimeters of mercury. What is this pressure in atmospheres? So it starts at 688, and we have to convert it to atmospheres. So we're going to use millimeters of mercury and atmospheres in our conversion factor. One simple conversion. 688 millimeters of mercury to start, 1 atmosphere on the top, 760 millimeters on the bottom. The units millimeters of mercury cancel, and we get the unit of atmospheres. The math becomes a simple division problem. 688 divided by 760 equals 0.905 atmospheres. So when you fly in an airplane, the pressure inside the cabin is roughly 90% typical atmospheric pressure. Now, what is standard pressure? 1 atmosphere, or 101.3 kilopascals. What is standard temperature? 273 Kelvin. When we have standard temperature and pressure, we get to use a valuable tool in chemical calculation. At standard temperature and pressure, all gases, no matter what they are, will have the same volume if there are the same number of particles. So let's say I have 1 mole of gas particles at the same temperature and pressure as another mole of gas particles. They automatically will take up the same volume. That volume of that 1 mole of gas particles is going to be 22.4 liters. When? 22.4 liters at standard temperature and pressure. This is called the molar volume of any gas. And this is very useful in gas stoichiometry. How will you know when you're using gas stoichiometry? If the stoichiometry problem involves any of these covalent compounds or any of these elements, you may be able to use this as a conversion factor. So let's do some stoichiometry problems to give you a little bit of practice. All right, here's an example of gas stoichiometry. For the reaction at STP, check it out. I told you STP. That's a big hint that you're going to be able to use 22.4 liters equals 1 mole. CH4 plus 2O2 becomes CO2 and 2H2O. Well, let's have a look. Methane, right there. Methane's a gas. You already happen to know oxygen's a gas. And of course you recognize that carbon dioxide is a gas. At STP, probably water is not a gas. At STP, water is probably a liquid, or it could be a solid, or somewhere in between. So these three, 1, 2, 3, I can use that 22.4 liters equals 1 mole relationship in the stoichiometry. So let's read the problem. React 7.5 liters of methane. How many liters of oxygen are used? And how many liters of carbon dioxide are made? So methane is here. In the balance reaction, there's a 1, an implied 1 here. So for every 1 liter of methane, 2 liters of oxygen are produced. So for every 7.5 liters of methane, 15 liters of oxygen are used up. 1 liter uses up 2 liters of oxygen to form 1 liter of CO2. So if 7.5 liters of methane are used up, 7.5 liters of carbon dioxide are made. We didn't have to go through moles. We didn't have to use the 22.4 liter conversion factor. When we use gases, the coefficients in the balance reaction also can be used as moles. Pretty cool, huh? Let's try another one. Here's another reaction. C2H6. That's ethane gas. Plus 7/2 O2 gas. Form 2 CO2 gas and 3 H2O. Well, at STP, that's probably a liquid. That's probably not a gas. All the mole relationships involving gases are also volume relationships at STP. So if 2 moles of C2H6 react at STP, how many liters of oxygen are used? How many liters of CO2 are made? Okay, it's going to be very simple. I'll start with 2 moles, but this is a gas, so I can use that as 2 liters. 2 liters C2H6. And let's convert it into oxygen. For every 1 C2H6, 7/2 O2 is used up, So 2 times 7/2 equals 7 liters of O2 used. For CO2, we will again start with 2 liters of C2H6. And this time, there's 2 CO2s for every 1 C2H6. So I've got 4 liters of CO2 made. Simple gas stoichiometry using the molar volume of a gas, all because it occurs at standard temperature and pressure. Be sure to look for that. Now, there's one more problem I want you to take a look at. And it comes from this knowledge of what we know about gases. We can all imagine and we can all agree that gases expand to fill their containers. So if I put some gas in a container, everywhere inside the container there will be gas molecules. There won't be pockets of empty space. They will be evenly distributed because they will expand to fill the container. That means we are able to do problems like this. I have a container that I represent gases of 3 different types, A, B, and C. Gas A is pink, gas B is black, and gas C is yellow. Now each of these gases expand to fill their container, so they completely mixed. They are miscible gases. That's one property of gases that helps us out tremendously, their miscibility. So these gases are completely miscible. They're always moving at the same temperature. They're all moving constantly. So the total pressure in the vessel, if it's 6 atmospheres, then each of these gases contributes to that pressure. Each of these gases have a partial pressure. And we can determine the partial pressure due to each gas. So let's figure out the partial pressure due to gas A. Let's see, gas A has 4 particles. 1, 2, 3, 4. Out of a total of 14 total particles. And I take that fraction times the whole pressure, and I get 1.7 atmospheres as the partial pressure for gas A. Let's look at gas B. Gas B, 1, 2, 3, 4. Also 4 particles out of 14. So 4/14 of the 6 atmosphere of pressure is coming from gas B. So that's 1.7 atmospheres of pressure. And gas C, 1, 2, 3, 4, 5, 6. 6 particles out of the total of 14 is gas C. So 6/14 of the pressure equals 2.6 atmospheres. Now if you total these up, 1.7 plus 1.7 plus 2.6 all adds up to 6.0 atmospheres. This pressure came from the partial pressure exerted from each of the gases in a mixture. This is called Dalton's law of partial pressures. If you have a mixture of gases, the total pressure will be the sum of pressures of individual gases. So that's the introduction to gases. You have some problems to work out on your worksheet, and you should take that time now to do that and make sure you turn it in before the end of the period. And also do some practice problems from your study guide tonight for homework. Good luck, gentlemen.